One of the particular places where this alternate format is used to find the derivative, one particular function variety where this is very helpful is with absolute value. I want to take a little bit of a brush through, a review of absolute value to make sure we're all looking at it in the proper fashion. Many students learn absolute value as, if you have the absolute value of a positive number, just write it down, you're done. The absolute value of 9 is 9. The absolute value of 15 is 15. The absolute value of 0 is 0. So if the value in question is greater than or equal to 0, the way you find the absolute value of that number is just remove the absolute value bars and be done with it. But the absolute value of -2 is 2. Yeah? What students learn, and this is not the correct way to think about it, what students sometimes learn is to find the absolute value of something that's less than 0, just remove the negative sign. That's not the best way to think of it. And see if I can sort of illustrate that. What is the absolute value of 3? Let's do it this way. Yeah, let's do 3 minus pi. Now, there are some students that will learn this. They will learn the way you find absolute value is you change the negative to a positive. Their rule for absolute value is change the negative to a positive, and they don't even think about it. Well, that's a problem. If you use this is now erroneous. If you use that wrong rule, you get 3 plus pi, which is approximately 6.14, and that's not correct. Because what is supposed to be correct is this is 3 minus pi, which is negative 0.14 approximately. And so this is approximately 0.14. That's the correct result. That's not. And so the rule of change the negative to a positive doesn't work. There are some other finer point details, but this is the net effect. The way you work absolute value is, yes, if the value of x is greater than or equal to 0, then all you do is remove the absolute value bars and you're done. The absolute value of 10 is 10. The absolute value of 50 is 50. The absolute value of 0 is 0. If the number in question is greater than or equal to 0, just remove the absolute value bars. But if the number in question is less than 0, suppose we want to find the absolute value of, let's say, -4. The rule is you don't take the negative sign away. You add an extra negative sign, simplify. Add an extra negative sign and simplify. -4 is 4, and that's the correct result. The absolute value of -15 is -15, which is 15. That's the correct result. You're thinking, you're just making this complicated. This, 3 minus pi, falls into this category. 3 minus pi falls into this category. So you don't change the minus to a plus. That's like the 5th grade way of thinking of absolute value. You don't change the minus to a plus. What you do is you throw an extra negative sign in front and you simplify. This is -3 plus pi, which is pi minus 3, which is approximately 0.14, and that was the correct result. So if the value in question is less than 0, you put an extra negative sign in front of it and simplify. Now, all this is just the way to think of it. This is the actual definition of absolute value. This is the actual definition of absolute value. Now, we're interested in absolute value of x minus 3, so it works the same way. If this quantity is greater than or equal to 0, then the absolute value is just x minus 3, right? Suppose I choose x to be 10. 10 minus 3 is 7. 10 minus 3 is greater than or equal to 0, and so that's 10 minus 3 is 7. Answer is 7. But suppose I choose x to be 1. If x is 1, this is 1 minus 3 is -3. 1 minus 3 is not bigger than 0. If x minus 3 is less than 0, You don't change the minus to a plus. You put an extra negative sign in front of it. And that will always give you the correct result. If x is, let's make it easy. Suppose x is negative 10. Negative 10 minus 13 is negative 13. Our answer better be negative 13. All right? So if x is negative 10, negative 10 minus 3 is less than 0. So this is negative 10 minus 3, which is negative 13, which is 13, and we're good to go. So that's the long of it. The short of it is that's the rule for absolute value of x minus 3. Now, with that, now we're going back up to the calculus problem. I'm going to use this expression. So we want to find the derivative at 3 of this expression. So this is the limit as x goes to a in our problem is 3. Right? The number in question is 3. I need f of x. F of x is, well, I'll write it out here. Well, a in our problem is 3. So this is equal to the limit. X goes to 3 of f of x is right here. Minus f of a, right? F of a. Well, what is f of a? What is this function value evaluate when a equals 3? What is f of a? In this particular problem, 3 minus 3 is 0. That's f of 0, which is 0. All over x minus a. X in our case is 3, or x rather, a in our case is 3. So this finally simplifies down. Absolute x minus 3 over x minus 3. That's what we get from this computation. And any computation of this variety will end up with something similar to this. The particulars will be different, but this will be the basic structure. Now, direct substitution gives us 0 divided by 0. We need to do some algebra, but you can't factor with absolute value. The only thing you can do with absolute value is fiddle around with this definition here. And so, whenever you have absolute value, a limit, absolute value, and you get 0 divided by 0. Limit, absolute value, you get 0 divided by 0. Now watch, if this is limit, let's go off to the side here. Suppose this, suppose this were, just pick a number out of the blue sky, 12. If I want the limit as x goes to 12, you just plug and chug. 12 minus 3 is 9. Absolute value of 9 is 9. Over 9 minus 3 is 9. It's equal to 1. If it's something other than 3, if you get other than 0 divided by 0, that's wonderful. What if I were doing the limit, again, pick another number out of the blue sky. Negative 8 of x minus 3 over x minus 3. Suppose we're doing negative 8. Again, pick a number out of the blue sky. Just substitute, simplify. So this is negative 8 minus 3, absolute, and then negative 8 minus 3. Well, what is that? That's absolute negative 11 over negative 11. That's negative 1. So if you get an answer, that's wonderful, you get an answer. But if you get 0 divided by 0, this is the procedure. If you get 0 divided by 0, this is the procedure with absolute value. You must do the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. As x approaches 3 from the left, we're talking about x's equaling things like 2.9, 2.999. These are numbers less than 3. So how does absolute value work? If I'm approaching 3 from the left, these are numbers like 2.9, 2.99. Those numbers are all less than 0. For any number left, when you approach from the left, you take absolute value and replace it with that expression. As you approach from the left, you get this numerator changes to negative parenthesis x minus 3 over x minus 3. They cancel, you're left with negative 1. So the limit from the left is negative 1. Then you also check the limit from the right. As you approach 3 from the right, you're talking about numbers like 3.1, 3.001, 3.0001. And for all those numbers, 3.1 minus 3 is bigger than 0. 3.001 minus 3 is bigger than 0. For all the numbers in this limit approach, you're in category 1. And when you're in category 1, absolute x minus 3 gets replaced with just x minus 3. So for numbers in this approach, the numerator is just x minus 3. There is nothing to do to it. And that reduces, it's just 1. The limit from the left is -1. The limit from the right is +1. If the limit from the left and the limit from the right do not equal, that means the unrestricted limit does not exist. This limit, the unrestricted limit, does not exist because the limit from the left and the limit from the right do not equal. The unrestricted limit does not exist because the limit from the left and the limit from the right do not equal. The point of this argument is not that I'm going to expect you to work something like this out. I'm not. I'm not going to expect you to work something like this out. But there is a larger point to be made, and that's what I'm after. The larger point is this. You know what the graph of this function looks like. Or you should. This is the basic absolute value function shifted 3 units to the right. And we were trying to find the derivative at a equals 3. And what this says is the derivative is this limit. Since the left and right hand limits do not agree, what we conclude from this is the limit, as x approaches 3, of absolute x minus 3 over x minus 3 does not exist, which is to say the derivative does not exist. However, the derivative does not exist at 3. If we took this, we saw this, if you chose a number other than 3, you would get a solution. At 3, the absolute value function does not have a derivative. At 3, this absolute value of x minus 3, absolute x minus 3 does not have a derivative. That is to say, at this point. That point has a special name. It's called a cusp. And this is a specific case of a larger notion, which is what I'm after. What I'm after is this. Any function, there's nothing magic about absolute x minus 3. There's nothing magic about absolute value. Other functions have this phenomenon. Any function, if it has a cusp, any function that comes to a point, any function having a cusp, the derivative of the function does not exist at the cusp. Everywhere else, the derivative is fine. At the cusp, the derivative does not exist. Derivative of a function does not exist at a cusp because this limit will not exist at the cusp. And so again, there's nothing magic about absolute value. Many other function types have this particular phenomenon. And so generically we say this. If this is a function, comes to a point, and then moves on, at that point, f prime, if this is y equals f of x, f prime of x does not exist at that value. This derivative does not exist if it comes to a point. The derivative does not exist at a cusp. If a function hits a cusp, there is no derivative there. We will use this phrase. The function is differentiable. The function is differentiable. The function is differentiable means the derivative exists. The function is differentiable means the function's derivative exists. But if there's a cusp, there is no derivative. So when we say the function is differentiable, what that means is this does not occur. So let's make that in actual words here. The word differentiable means the derivative exists. If we say the function is differentiable on an interval, that means the derivative exists at every value in that interval. It's similar, it's related to the notion of continuity. We have continuity at a point, and if we say the function is continuous on an interval, continuity, continuous on the interval, means there are three things the function doesn't have: no holes, no jumps, no vertical asymptotes. So when we say the function is continuous on an interval, we mean on that interval, no holes, no jumps, no vertical asymptotes. If we say the function is differentiable on an interval, that means also no cusps. Differentiable means no cusps. A function is differentiable on an interval if the function does not have any cusps on that interval. Now, absolute value is fine. If I'm using absolute value of x minus 3, if I'm talking, this is 3. If I'm talking about this function on the interval from, let's say, 4, let's make it an open interval. If I'm talking about this function on the interval from, let's say, 4 to 7, then yeah, there's no problem. There are no cusps, there are no holes, no jumps, no vertical asymptotes. Everything's fine between 4 and 7. If I'm talking about between, say, negative 8 and -1, then there's no problem between -8 and -1 because there are no holes, no jumps, no vertical asymptotes. The function is continuous here. So let's talk about this function from -8. So this function, f of x, equals absolute x minus 3 on the interval from -8, let's say -8 to +7. So here's my little graph here. Here's 3. There we go. There we go. Let's suppose this is -8. Let's suppose this is 7. Is this function continuous? Is it continuous on the interval? Continuous means between -8 and 7. Now outside there, I don't care. But between -8 and 7, continuous means no holes, no jumps, no vertical asymptotes. Are there any holes, any jumps, any vertical asymptotes between -8 and 7? No, there are not. This function is continuous from -8 to 7. Are there any cusps between -8 and 7? Yes, there is a cusp between -8 and 7. This function is not differentiable on the interval from -8 to 7 because there is a value where there is a cusp. This is a value where the derivative fails to exist. Differentiable does not mean the same thing as continuous. Differentiable means no cusps. Continuous means no holes, no jumps, no vertical asymptotes. They're related, but they're not the same thing. All right? So differentiable means no cusps. Continuous means no holes, no jumps, no vertical asymptotes. All right? So that's what we mean when we say the differentiable. Differentiable means no cusps. There are other functions besides absolute value that have cusps. Absolute value is probably the most common, but it's not the only time that can happen. So understand those notions, and that'll help you because later on we're going to have a requirement that a function has to be continuous and it has to be differentiable, and you'll know what that means now.